Hanauma Bay in Oahu, Hawaii is classified under Hawaii's Clean Water Act as a Class AA water, which is to remain in its most natural, pristine state without any source of pollution. Conversely, Hanauma Bay is Hawaii's most populated swimming area, attracting millions of tourists worldwide. But of course, we are not in Oahu, we are in Griggs Reservoir in Columbus, Ohio. But that's okay, because while this is a riverfront and not a beach, it's still it sets the scene. In the summer, beaches attract copious amounts of tourists looking to enjoy the weather, the water, and the views. To protect themselves from the wrath of the sun, they use sunscreens that contain UV filter chemicals made from petroleum. One of these chemicals of interest is called Oxybenzone. In Hanauma Bay, Oxybenzone has been found in the water in very high concentrations after washing off of tourists from swimming or in beach showers or just overzealously using aerosols. Studies have confirmed that Hanauma Bay is suffering contamination from Oxybenzone. These studies have also proven that beach showers are even a point source due to the runoff not being treated using any kind of water infrastructure and just letting them freely drift off into the bay. This pollution has led to many ecological effects such as ocean acidification, coral bleaching, toxicity to marine plants, and endocrine disruption in multiple species. The observed effects of oxybenzone pollution have caused the state of Hawaii to ban the sale of petrochemical sunscreens, and also funding the education campaigns and development for Hawaii-compliant sunscreens that use alternative UV filters. While this is promising, this may likely remain an issue, especially outside of Hawaii in very tourist-heavy areas. For this reason, I'm creating a model to predict the transport of oxybenzone and other chemicals through a beach and bay system. The objective of constructing this model is to accurately predict the concentrations of oxybenzone at any point in time and at any point in the system. Hello, rowers. This model should be temporally variable so we can evaluate different tourist flows. It should be constructed in such a way that we can evaluate it using different initial conditions, such as if we wanted to measure a different system. However, due to the availability of literature and data, we're going to be using Hanauma Bay to construct the model first and use the existing data to verify it.
As far as our options go, there are a couple different approaches we can take. For one, we can take a Fugasti model. A Fugasti model uses an equilibrium approach, so it will tell you what goes on after a very long amount of time. So in this case, if I have a little pond with my sea monster here, and I drop a car battery into this pond, what would the concentration of lead acid be after a couple of weeks? The answer to that question will be very easily available through this Fugasti model approach. However, if I wanted to come back and put more car batteries periodically, say I put this car battery in on day 1 and I put this one on day 2, day 3, day 4, day 5, what's the concentration at day 3 in the soil? I don't know. It's a Fugasti model. A couple of things that make Fugasti models implausible for us is the fact that, one, it's required for us to use something temporally variable for this course project, and two, we have different tourist flows. So we have different amounts of people coming in at different times because this is in fact a commercial beach. So if we want to measure the concentrations at any point in time, what we can use then is advection and diffusion models. Advection models are described by the bulk transport of fluids, so this could be something as simple as sediment being carried down a stream. Diffusion, on the other hand, measures the transfers of particles from areas of high concentration to low concentration using Fick's law. This is sometimes used for the case of making things like carbon steel, but in our case we're going to model the transport of oxybenzone through the soil and water boundary by seeing how much will go through the soil into the rest of the water. To construct the model in Hanauma Bay, we have a 2-compartment system with soil and water, and we're going to measure both the emission that tourists create, and then we're going to measure the patterns between the two and how concentrations flow. Concentrations can move throughout a couple different ways. One rate of emission is if a tourist comes along and uses a beach shower and washes off some sunscreen from their skin. and that goes into the sand and eventually may diffuse into the water. That emission term will just add mass and subsequently concentrations to the soil system. Another way oxybenzone can enter the environment is washing off from swimmers. So if our tourist here wants to take a swim, that missed, but that oxybenzone can get into the water. We have a couple other considerations to make. First, the soil infiltration. It would take a while to get from a beach shower to the soil water horizon just for the sake of how big of a beach it is. But because beach sand has very low organic content, low retention, and very rapid infiltration, we can assume that the oxybenzone concentrations in the soil part of the system are constant because it can infiltrate that quickly. Another consideration we have to make is tidal patterns. Because Hanauma Bay is not a closed system like a pond, it's more of a pond that also kind of is connected to an open ocean. Immediately surrounding the beach, Hanauma Bay has a relatively shallow swash zone. This is home to coral reefs and wildlife and snorkelers. During some parts of the day, tidal patterns can cause water and subsequently chemicals to get trapped in that swash zone. So that's the main concentration that we're going to be working with. There are also tidal patterns that will take water out of the swash zone into the rest of the bay. This is called a flushing condition. Flushing conditions only happen during certain times of the day, so during those times I can run a diffusion model to see how much of that oxybenzone escapes into the rest of the bay, and subsequently out into the open ocean. Now that we've constructed a basis of the model, we can use MATLAB. Now that we have an idea of what the model is going to look like, we can actually get into MATLAB. This script uses a local function that runs all the diffusion equations every hour, and that local function is being called every single hour through a couple different nested for loops. Those for loops are just to track the time. To start our input parameter, I want to ask how many weeks will you run the model. Even while peak tourist season is a couple months, Hanauma Bay limits visitors to 1,500 a day. That makes my life easier because I can just put in 52 weeks and assume that it's a constant rate. And then we have a few different parameters that measure what week it is, what day of the week it is, and what hour of the day it is. I should have used date time, but that's fine. We then initialize the mass of oxybenzone in the soil and the mass of oxybenzone in the water. To run the model, we use a couple different nested for loops that run 24 hours a day, then for 7 days a week, then for however many weeks you want to run the model. The reason I did it this way is so that I could measure the different flushing conditions and the different tourist dwellings, because nobody is allowed to show up in Hanauma Bay at 3 a.m. That's why I have these temporal parameters such as tide toggle, which gives me the flushing conditions that happen from around 4 to 6 a.m. and then 3 to 7 p.m. When the tide toggle is 1, the script can check that it's under flushing conditions, and then we can run the diffusion model. We also have two different toggles for emission terms because tourists are only going to show up when the beach is open. We have the beach open from around 7 to 4 and Wednesday through Sunday. And we're going to track those days and hours through the nested for loop. Inside this local function is where we actually run the model. That's where we have all of our constants stored and all of our parameters stored so they won't be an unnecessary output. Our first calculation is how much oxybenzone will get emitted from a tourist to the water itself. For that we have a couple different estimations, such as the amount of sunscreen that goes on one unit area of the skin, and then how much of that goes on the entire body, and then how much of that might contain oxybenzone, and then how much of that might wash off of the skin afterwards. To calculate each emission term, we take the oxybenzone per person, and then we calculate that by the tourist volume, and then the wash-off rate, and then some proportion of how many of the tourists per day will actually use a beach shower versus will go in the water versus will use an aerosol. I'm just going to assume aerosols are a very low number because it's going to be very hard to model like the plume of, if I spray my arm, is that going to go in the water or is it going to go off in the distant air or anything like that. After we've got our emission terms, we're going to check to see if there are actually tourists on the beach for them to emit. So that's why we have this little if statement here through the different toggles from the emission of the hour and to check if the beach is open that day. If that's not true, there are going to be no emissions for the day, and they can just calculate the concentration as normal. After we calculate the emissions from each tourist, we can then calculate the diffusion between the bounds of the system. To do that, we use good old Fick's law, and we go ahead and calculate using our diffusion parameters. After we calculate the diffusive flux, we can calculate the new concentrations of what's in the soil after estimating how many particles have moved which and where. After we've determined the diffusion from soil to water, we can then determine the diffusion between water and water using the hydrologic transfer. This is using a similar equation, but because there's no soil or organic retention involved, it's just the concentration of water moving from the swash zone to the rest of the bay. And this is only active if the tide toggle is 1. So this diffusion is only happening when the tide is under flushing conditions. After going through each of these terms, we have the output of the massive oxybenzone in water and in soil. Through the nested for loops that we talked about earlier, we stored the output variables into a vector. These vectors will allow us to visualize what the concentrations look like over time. And if we run the model for 52 weeks, we find that the concentrations just slowly keep increasing from the emissions. It seems that the chemical load of oxybenzone is so great that it is accumulating within the bay. This means that the bay is unable to flush out the chemicals under the current tourist load, which is bad news. So after running the model for 52 weeks, we got up to about 1.65 micrograms per liter of oxybenzone in the soil, as well as 1.1618 micrograms per liter of oxybenzone in the water. We actually have data from 2018 of sand and water concentrations before the sunscreen ban went into effect. This is actually the same article that informed the decision to actually create the oxybenzone sunscreen ban. Their readings were about 12 micrograms per liter of soil and about 5 to 35 micrograms per liter in the water. That's actually not bad. I'm within an order or so. I'm actually quite impressed by that. The question I had after running all that data is that if you took all of the tourists out of the equation immediately, was there a time and point where you could get back to sort of normal concentrations? Hopefully 0. I theoretically have the right model to do that. I just need to change the mass of oxybenzone initially, and then I need to remove the emission terms. After running that model, however, it didn't really work and it just flattened out. This gives me the impression that the flushing conditions part of the script didn't actually work. Oh my god. Oh my god, I forgot to index the vector. So either the flushing condition is so small it's negligent, or something about it still doesn't work. I'm still not getting much of a different answer here. So, we found that even limiting the tourist volume and capacity of Hanauma Bay still leads to a steady increase in oxybenzone concentrations over a long period of time. This is likely due to the geography of being trapped into the swash zone, as well as just the very large amount of tourist volumes. What this means for the bay is that these chemicals are getting trapped inside the bay, and that will continue to harm the coral reefs and the existing wildlife and the marine plants and the water itself continuously. This might, however, require further hydrologic study, as I just used a diffusion model across certain tidal patterns, and that may not be actually accurate for the chemical transport throughout the bay. However, this model was still able to prove that there is accumulation, meaning that these tourist volumes are harming the area regardless. This model should be a reinforcement for the fact that changes are already being made, and that is good news. The sale of petrochemical sunscreens in Hawaii are being banned for this very reason. However, this is likely a problem in other situations, such as different places that don't have bans on petrochemical sunscreens, or similar geographies but with different chemicals. I would hope that this model inspires further research and investigation into these different use cases. And hopefully there will be a time where we don't have to worry about things like coral bleaching. Thanks for watching.